Good morning, viewers. Today we are going to see about the Anova analysis. First, Anova analysis is used for a statistical method like max in for a master degree students or a PhD students in the construction studies. They mostly use for an Anova studies. Okay, let me see what is the Anova analysis about that. Okay. What is an ANOVA? In this slide, we are going to see what is an ANOVA. ANOVA is a powerful analytic tool used for statistical calculation, like for a large number of data we have get, and from the data we have to analyze. Depend on some dependent variable and independent variable will be there. Dependent variable means it depends on something relevant to this, and independent variable is not relevant to some like that. If you check for an students in the class, um, depend on a height, the weight may be varies like that. It depends on the weight is depends on height like that. It's a dependent variable. Independent variable like comparing the height and with ranks of the students, it cannot relevant to the variables like that. It's an independent variable, and dependent variables are classified. From that, we are going to analyze the means and statisticals using this Anova method. Okay. Next, we are going to see how to analyze using this Anova method. Yes, Anova is developed by an R.A. Fisherman in 1920. R.A. Fisherman is a British mathematician and is also a biologist. Okay. ANOVA is also known as F test, which is based on F distribution. Yes. Um, in this ANOVA table, we can calculate using this F test method for the for getting the test of hypothesis values. Mostly, test has t-test mostly used in a statistical method like t-test, f-test, and z-test. Mostly, f-test is used for an ANOVA calculations. Comparing for an two different mean values like two groups we can be classified to analyze the test of hypothesis values. Okay. In an ANOVA, okay. ANOVA is mostly known as a calculation for a test of hypothesis. Like there is no significant difference between the main values, or there is a significant difference between the main value. Like alternative hypothesis and null hypothesis, we can classify using this ANOVA method for getting the result for the difference comparing these values. Like ANOVA is classified into two methods, like one-way classification and two-way classification. One-way classification as a method like completely randomized design CRD. Okay. Like one-way classification is nothing like that, calculating like row-wise or column-wise, like only one way only. Like if we calculate for an column only or a row column only like that. For two-way classification, we can calculate using like column wise and row wise, and both ways we can be calculated. Like comparing these two, we can be classified for the test of hypothesis value. Like two-way classification has a method like randomized block designs or BD method known as. Okay. Statistical technique is used to compare the means of variations. Like comparing the two samples of populations, we can compare it, and it is known as an ANOVA test. Okay, we can let's see. It's a theory part. We can see the some of the references, and we can go to next. Okay, types of ANOVA. ANOVA is I say as a one-way classification, two-way classification as considered. From that we can it can be analyzed from the next part. Okay, we can explain it next slide. Next slide is about completely randomized designs. In this topic we are going to see like the is a golfer has five groups divided into from the five groups we can compare how the distance will be, the goal will be delivered. Like that we can compare using this. Like this is a completely randomized designs, like column wise we can calculate it. Next, ANOVA significant columns in ANOVA. Okay, In Anova tables, there is a column like sources, degree of freedom, as we have mentioned here, right? Sources, degree of freedom, and sum of squares, and mean sum of squares, F statistics, and p values. This is the main sources we have plotted in Anova tables for one-way classification and two-way classifications. Next, next is row-wise what is classified for Anova tables, like factors we can analyze, and errors and total. Like for that factor, error, totals we can classify for degree of freedoms, mean sum of squares, and F tables like that. Okay. And for F ratios, there is a formula like mean sum of squares between factors by mean sum of squares within. Okay. From you can be helpful easy for doing seeing these problems, can be helpful. Okay. Next, the ANOVA testings of hypothesis. Null hypothesis. Null hypothesis is known as like H naught. There is no significant difference between the mean of groups. Like alternative hypothesis is like H1 or H we can be classified like that, and it's an opposite, like there is a significant difference between the sum of groups. The difference should be there is something difference between the two groups, we can be classified like that. Like this is a example for the tables, like we are going to plot for the one-way and two-way classifications. Like degree of freedom, sum of square is known as net. DF is known as degree of freedoms, and SS is the sum of square. MS is the mean sum of squares. Okay, and mean sum of square is as a formula like SS divided by DF, and we have to calculate for an F ratio. Like we can be useful for doing these problems. Okay. Like that is sources in between a groups, error and total dependent in a row wise. Okay. This is an example for an ANOVA tables. This is how we can be plot in problems. Like we can see there is degree of freedom like k minus 1 highlighted for k is known as how many rows or columns in the treatment, between the treatments we can be classified for an km, and n is known as total numbers, how many sources are in this in questions, how many n in tables we can classify. Okay, it can be very helpful for doing seeing this problem. Any problem we can see easily understandable. Okay, and it can there is another formula for total sum of squares. There is a yij square minus g squared by n. It is an okay, g squared by n is the main very important point we have to keep in knowledge, understand. This is the most common term. This is the most common term is used for every formula we have been applied. Like we can see in these problems in a sum of squares. In this formula they have implemented g square by n. Like that we can every formulas mostly we can use g square by n is correction factors. Is between a sample sum of squares. For calculating is a formula for ti square by ri minus t square by n. Okay. Okay. Like you can see there is this graph, this diagrams you can see this is a h naught and this is area, this area are h1 area, like reject h naught. Okay, this is a positive h naught, this is a negative h naught, acceptance regions. Okay, and like in this formula you can see f critical is greater than f statistical is an h naught, if f critical is less than f statistical it is an h1. Okay, you can see on example problems First we can read the questions. A completely randomized design experiment with 10 plots and three treatments gave a following results. Okay. Okay. They have this question. They have tables. They have given a 10 plots. From the 10 plots, they have classified three different treatments. Like any fertilizers, they have used like treatments. A treatments have 5, B treatments have 4, C treatments have 3, and again A treatment have 7, and like C 5 have 5, C have 5, A have 3, and B have 4, A have 1. Like for the three treatments, they have classified for 10 plots what is the yield values. Okay. Okay. And they have analyzed the result for treatment effects. Okay, they have mentioned as a treatment effect. So we have making a tables for a treatment like A, B, C for the in a row wise, and classifying a treatment wise, like for A as B, and next to A we have classifications 7 they have plotted, and like for another A as 3, and another A for 1. Like we can keep for like 3 and 1 or 1 and 3. We can randomly keep. There's no issue for this one way classifications. Like we are going to see calculate for column wise. So there is no issues. Like for B they have plotted for B treatments. I have a 4 and another 4 and another 7. Like that we can classify for this A, B, C. Okay, like TA is known as nothing, like some of these replications, like yield, some of these yields we have classified like 5 plus 7 plus 1 plus 3 is equal to 16. Adding these 4 values we can get a 16. Like adding these 3 values we get a 15, and adding this 3 value we're getting a 9. This is known as a TI, a treatment of this treatment values. Next we are going to do a Spire. It's mostly useful doing for formula usage, so we are going to use for TI squares. Like that they have calculated for this squaring these values, 15 square, 9 square, like that they have calculated. Okay, they have plotted these questions. Like we have to first we have to classify what will we get for this result. Like this is the final result we need to have. This is a H0 or H1 we are going to analyze using this Anova methods. Okay, and this question we can define H0. There is no difference in the effect of treatment. Like in these questions they have mentioned to analyze the effects of treatment. So like that, depend on the question we are going to predict the Anova test, null hypothesis and alternate hypothesis, like H0 H1. Okay, for H0 we have to apply there is no significant difference present in the effect of treatment, and H1 is the opposite, there is a significant difference in the effect of treatments, like that. A level of significant is we generally taking as a 5%, like that they have taken a 0.005. Okay, and we have to calculate for an grand totals. Grand total is known as a G, and correction factor is known as a G square by N. Okay, it can be mostly used for an every problems. Like G is nothing like TI. Calculating the TI is like we get some of the column values like 16, 15, 9 for E treatment 16, B treatment 15, and C treatment 9, and its total is equal to 40. Okay, and the N value is known as number of samples. Like we have plot as a 10 plots, so it's known as a 10. Okay, and correction factors we have calculated like G square by N, like 40 square by we get a 40 square by 10. Okay, it's 160. Okay, Okay, next is total sum of squares. TSS, we can calculate is a formula as yij square minus g square by n, as we seen in our last slide. Like this formula is applied. Like yij is known as for every single values. Like we get 10 plots, right? For 10 plots, they have some 10 values, 10 yield values. For every value, we are going to square and addings, sum of squares, like we are adding with minus correction factors. We are going to get this value. Like for every value, like in the question we have get 5, 4, 3. Like for 10 yield values, they have calculator and separating with this correction factor. Okay, this is known as total sum of squares. Okay, and we get total sum of square TSS equal to 40. Okay. TSS equal to 40. Okay, sorry, little bit mistakes. Okay, between sample sum of squares. Like for one way test, we can get one sample, sample sum of square we can be calculated. For two-way sample, two-way classification, we can get many values. Okay, okay. Like we have only the one treatments, so we are going to add this treatment values, and by dividing the how many rows are in every treatments, we're going to calculate like ti squares for sum of squares. Like first a value we get 256 ti square values, and they have four columns, so we're going to have 4. And for next 225 is 225 is b value ta square value, and it has 3 columns. Okay, and for c values as 81, and for this they have 3 columns. Like that we're going to implement these problems, and with minus correction factors. Okay, we get an R1 equal to 6. Okay, we get TSS value and R1 value, and we are going to calculate for the sum of square errors. Okay, as a total value we get, and between a sample value we get calculate for an error by applying this above formula, or like SSC is known as a sum of square of errors. This formula has a TSS minus R1. From separating this, we get error value 40 minus 16 is known as 34. Okay. From above to calculate, separating this, we get a error value. Okay. Okay. Next, we are going to plot this Anova table. Like that, from source, degree of freedom, sum of square, mean sum of square, variance ratio, we are going to plot in a column wise. Between our treatments, errors, total, we're going to plot this row wise. For between treatments, there is how many treatments, like k is known as like row values. Like we have a b c as a 3 treatments. This is known as a k value, and for degree of freedom, this has a k minus 1, like 3 minus 1 is 2. Okay, for errors, error is has a formula n minus k. N is a total number of samples minus this treatment, how many treatments, like 10 minus 3 is equal to 7. Okay, total is a formula for degree of freedom n minus 1. Okay, we get a 10 minus 1 9. Sum of squares, like previous slide, we get a value of between a treatments and 6 value, and for error 34 and total 40. Okay, mean sum of square is nothing like for sum of square divided by degree of freedom. Like we get an 6 divided by 2, we have get a 3 value as a mean sum of square. Like that, for error 34 divided by 7, we get an 4.857. mostly we cannot we generally not calculate for a total value. It cannot be useful for the final result. So we can take up to for an error as a mean sum of square value. And for f ratio, we are going to calculate which is a greater value, like 3 is greater or 4.857. We have to compare between these two values, which is greater is being placed on the numerator value, like 4.857 is a greater compared to 3. So we have to plot this 4.87 as numerator for f value and denominator as 3. So we get a f value like 4.619. Okay. Next we are going to see about the table value. For table value, this is a formula, like we have to take for 5% as a 95% as a significant value. For that there is a formula f 0.05 as a 72 is nothing, like we have taken as a 4.87 as numerator. It will be the degree of freedom will be implemented in this first values, and denominator value will be implemented in the degree of freedom is implemented in the next values. Like if the between the treatments this R1 value is greater, like it will be the degree of freedom will be implemented in the first values. And if like its error value, if is in denominator, the degree of freedom will be implemented in the second value. For compare this value in a table, we get like in f table has an chart. From the table we can identify what is the value for this f 0.05 for 7 comma 2. We can get about 19.35. Okay, I can explain this how to identify this f table value in this next slide, in the next time. Okay, from that we can get about what is f ratio value and f table value. We can analyze. From that we can identify which is greater values. Comparing these two, like f table value is greater. So if f table value is greater, then we have to accept h naught. So we get a conclusions like there is no difference in the effect of treatments. Okay, like that we can analyze using this Anova table for an h naught and h1 values. Okay. Okay. Okay, in this table we can see how to identify the stable value for like you can see f tables 95 percentage, like 95 percentage we can analyze. Okay, we have get in the previous slide like for 7 and 2, for comparing this, like v1 is known as the first value and v2 is known as the second values. Like if we get two value, we can be see like 2 and 7. Comparing this we can get 4.27. For an actual, what we get is known as f table value is 7 for 2, we get a 19.4. Okay, like that we can analyze and get the table value using this f table chart and compare this. There is h naught or h1 value. Okay. Most generally, if f table value is not given in the questions, we mostly take like a 95 percentage significant value, and for that 0.05 we can take for the f tables. If suppose if they give for like the f table critical value as 0.01, we can be using this another 0.01 table for that, comparing the h naught or h1 values. And also for like we can see for also for f table for 0.01 percentage also we can see.